Okay. So looking at this picture that I've zoomed out a little bit because I drew it very large, we're going to be looking at a couple triangles. So we're dividing the thin lens equation here. We're going to be looking at PQO. So that would be PQO, this triangle there, and P prime, Q prime, and O. All right, so the thing to notice is that these are similar triangles. Therefore, we can relate their sides. And remember, similar has a specific meaning when you're talking about geometry. All right, so y over s we can say is equal to negative y prime over s prime. And that's negative, right? Because it's below the optical axis. And we can rearrange that so that we get a y prime over y relation being negative s prime over s. All right. So same goes for triangles OAF2. Go orange here. Well, I'll go blue. I'll go orange because we're going to use blue later. OAF2. So this triangle here, here, and here, as well as P prime, Q prime, and F2. Right? Those two triangles are similar. So we can also say that y over the focal length is equal to negative y prime over s prime minus the focal length. Right? So y, this length here, divided by the focal length, which is this length here, is equal to y prime over s prime minus the focal length. So that's that guy, right? Boom. Which we can rearrange again to get that y prime over y relation of negative s prime minus focal length over focal length. All right. So therefore, we can equate these two and divide by s prime to find a relation. So if we equate these two here, right, then we can see that negative s prime over s is equal to negative s prime minus focal length over the focal length. All right. And so dividing by s prime, is that what we said we were going to do? Yeah, divide by s prime. And we get s prime over s plus 1 equal to s prime over f. And divide by s prime, and you get 1 over s plus 1 over s prime is equal to 1 over the focal length. This here is the thin lens equation. Boom. Simple as that. All right. And we also already found the lateral magnification of a thin lens, right? We found it here, here. So lateral magnification is equal to y prime over y equals negative s prime over s. So I'll box that guy in. It's lateral magnification for thin lens. Tablet's either getting hot or low on battery. It's affecting the delay there. All right, so these equations apply both to converging and diverging lenses, and sometimes it's obvious if a lens is converging or diverging. But here are two statements that you can fall back on if it's not obvious. And while I read them, I'm going to paste this picture in here so that you can believe me that sometimes it's not obvious. So here's an image. So look at those guys and see if you'd be able to make an easy determination. Maybe you could. but here's a sentence that will help you. So any lens that is thicker at its center than at its edges is a converging lens with positive f focal length. On the other hand, any lens that is thicker at its edges than its center is a diverging lens with negative focal length. So take a look at those examples and confirm that that's the case there. So if it's thicker at its center than its edges, then it's converging. If it's thinner at its center than its edges, then it's diverging. Simple as that. So some of these weird wonky ones you might not be able to tell immediately, but there you go. And if you're curious what a ray diagram looks like for a diverging lens, we'll draw it really quickly here. Let's take this one as an example. And if you have parallel rays coming in, then they diverge. Right? And right at the center, it goes straight through. So that's the case if you have light coming in this way. And if you have light coming in the other way, well, light takes the same path, right? Light's path is reversible. So if you have converging light coming in this way, right, from some prior optical piece that caused it to do so, right, some converging thing, right? Maybe you have some converging lens back over here that's much larger, and it sent light through that started converging it this way. And you place this diverging lens before it gets to the would-be focal point there, right? So this is how optical pieces can combine to create interesting optical systems. So if you put this guy here, then and its geometry is, such, then you would get your parallel rays coming out there. So very interesting systems can be chained together or created by chaining together these lenses, these thin lenses. All right, that's it for this. Oops. The next step for us is to derive the lensmaker's equation, which is a thrilling derivation, I'll tell you.